Welcome to Next Gen Manufacturing, where we dig into the tech that's changing how things get made. Today, we're talking about a technique that basically takes a fundamental rule of manufacturing and just flips it completely upside down.
I mean, it sounds like a riddle, right? In a world that's all about efficiency and the shortest path from A to B, how on earth could taking a winding, spiraling route be faster than just going straight? Well, that is the exact paradox we are going to unpack today.
And here's our roadmap. We'll start with that paradox. Then we'll define exactly what trochoidal milling is. We'll get into its incredible benefits, look at what it actually takes to do it, see how it holds up at the microscopic level, and then wrap up by figuring out its place in the future of making things.
Okay, so let's dive right into that central idea and maybe break some old rules along the way.
You know, for ages, if you needed to cut a slot in a piece of metal, the logic was simple. Just plow right through it. A straight line, brute force attack. Makes sense, right? But that method puts a ton of stress on the cutting tool. We're talking massive heat buildup, tools wearing out way too fast, and it can even mess with the final accuracy of the part. It's the simple way for sure, but it is definitely not the smartest way.
And that brings us to the solution. So what exactly is this smarter approach all about?
Put simply, instead of just shoving a tool straight through the material, the tool path is a series of looping, circular cuts that look kind of like a spiral. Picture drawing a slinky moving forward on a piece of paper. That's basically it. Now, this lets a smaller tool carve out a much wider channel, which is cool in itself, but the real magic is in how it gets it done. And this right here tells the whole story. On the left, you've got the old way, high stress, heavy load, basically a fist fight between the tool and the metal. And on the right, you have the new way, these elegant circular cuts that just sip away at the material, dramatically lowering the stress on the tool. It's really the difference between using a battering ram and a surgeon's scalpel. So the secret sauce here has two parts. First, the tool only takes these tiny little side steps into the material. That's what we call a low radial depth of cut. But, and this is the genius part, it uses the entire length of its cutting edge while it does it. That's a high axial depth of cut. So instead of all the force and heat being focused on the very tip of the tool, the work gets spread out all the way up and down. So you can probably guess what happens next. This one clever trick unlocks this incredible chain reaction of benefits. And it really is a cascade. Because you have lower cutting forces, you get way less heat. Less heat means the tool doesn't wear down as fast, so its life is dramatically extended. Lower forces also mean the tool isn't bending, so your parts are more accurate. And since the tool isn't under so much stress, you can run the machine way, way faster, which just demolishes your cycle times. It's a win on top of a win on top of a win.
Let's just hammer this tool life point home because it is a huge deal. Think about it like this. It's like the difference between trying to draw with just the very tip of a pencil until it's dull versus shading with the entire side of the lead. By spreading that workload across the whole cutting edge, no single part of the tool gets beat up. The heat, the wear, it's all distributed, and that can mean a tool lasts multiples longer than it used to.
And here's the kicker for the bean counters. Since the tool is dancing around to create a slot that's wider than itself, you don't need a different tool for every single slot size anymore. One tool can handle a bunch of different jobs. And what does that mean? Fewer tool changes, less machine downtime, and more open spots in your tool magazine for other things. It's just pure, uncut efficiency. But, of course, a revolution this big doesn't just happen for free. There are a few key things you need to make this magic work. Yeah, you're not going to be doing this on some 30-year-old machine from the back of the shop. You need two critical things. First, you need a modern CNC machine that can handle really high speeds and, this is crucial, can adjust how fast it's moving on the fly. And second, you need the brains of the operation, specialized CAM software that can actually calculate these incredibly complex spiraling toolpaths. And that software is doing some seriously heavy lifting. This gives you just a little peek at the kind of math it's constantly running. It's figuring out the perfect cutter size for the job and then calculating the exact size of those little side steps we were talking about. Get these numbers wrong and you've got problems. So all that intelligence is just baked right into the software.
So we know this technique is powerful for regular size parts, but what happens when we shrink everything down to the microscopic level?
This is where trochoidal milling becomes an absolute superhero. When you're working with tools that are as thin as a needle, they are unbelievably fragile. A traditional brute force cut would just snap them in an instant, but the gentle, controlled forces of a trochoidal path mean you can actually machine tiny, super precise features without breaking your tools. It's a game changer.
But, and there's always a but, it's not a silver bullet. At this tiny scale, every little problem gets magnified. The slightest vibration in the machine, a hard spot in the metal you can't even see, any of it can be enough to snap a micro tool, even if your technique is perfect. So while it's possible, it requires an almost unbelievable level of precision and control.
In fact, there's kind of a rule of thumb in the industry. Once you get down to tools smaller than this, about 1/16 of an inch, things get really, really dicey. It's not that it's impossible, but it becomes prohibitively risky. Below that size, your machine, your material, your entire setup has to be absolutely flawless.
So let's pull all this together. What does it all mean? Well, it's the classic story. It's about working smarter, not harder. At the end of the day, trochoidal milling isn't just another way to cut metal, it's really a whole new philosophy. It represents a fundamental shift away from overpowering the material with brute force and toward outsmarting it with physics and intelligent code. It's all about getting better results, getting them faster, and doing it with less waste. And that really leaves us with a pretty exciting question, doesn't it? We've just seen how completely rethinking something as basic as cutting a straight line can set off this amazing cascade of improvements. So it really makes you wonder, as our machines and our software get even smarter, what's the next old-school brute force process that's just waiting for its smarter, not harder moment?